Oh, okay. Okay, are you okay with this being a recording?
Yeah, I'm okay.
Yeah, I think this is great. Okay, so we will get started. So today it's a great pleasure to welcome Dr. Khoa Luu from University of Arkansas, the main campus. So they have University of Arkansas have multiple campuses. So I think so I get to know him because particularly for our students here, they have been doing very well. His group. The other time when I visited Arkansas, I saw them, showing a demo. The first one is a facial recognition. I found that they have doing quite a cool stuff. And then later on, I started, followed some of his work. He actually doing computer vision image understanding. Is your lab's name, right?
Yeah.
CUIU. So I think that it's really a CVIU. So they're really about, apply this to the different, like a face recognition, and then doing the multiple object tracking. So I think Arbeit recently needed that. So you might be one to download the code and start play.
Yeah.
Very cool technology. Even the people I saw yesterday, even people can cross that. Some of them actually publish a paper on similarly, but not as deep as you guys do. Also applies this to the autonomous vehicle. So in generally, I found that his work is complemented with what we are doing very well, right? That's why I want to, invite him to come here to share with their work with us. So he's been very active, by the way. Also as assistant professor, I guess, but he already been in the community. Actually, index already goes to 30 something. In many other schools, 30 could go to a full professor now.
Oh, yeah.
So he's doing very well, very active, as an area chair for the CDPR 2024. Also, so I think he's kind of a model that many of you who want to be a faculty down the road, look at it. Okay. Well,
Thank you.
Yeah.
Thank you so much, Dr. Xi, for hosting me today and the student coming. It's my honor to give the presentation to the student. So I know Dr. Xi had a very deep dive in autonomous car industry and research. So that's why my presentation more about the perception for AV in this talk mainly. So my background is about AI, computer vision, and we try to apply it for perception, multi-object tracking, behavior understanding. A little bit further, I work in face recognition biometric for more than 15 years in my PhD, and then the work in CMU before I moved to U8.
Oh, you mentioned yesterday you got another PhD from CMU.
Oh, that is the long story. So I did my first PhD in Canada, and during my PhD, I moved to, I met my own boss in CMU, and I asked him, give me 3 months to visit the lab, like visiting scholar, and I stayed there for 7 years. Why I moved there, I was the boss doc, even though I was a PhD in Canada. And then I took my second PhD in CMU, in ECE, my first PhD in CS, and then I do my second PhD in signal processing because I love doing signal processing, and CMU is very good backgrounds there. But then my first daughter, my wife got pregnant. So my wife also PhD in ECE department in CMU as well. So I dropped off my second PhD. So I have 1.5 officially. So that is my long story. And last 3 years with CMU, I manage more about the project. That's why I was the research project director. More about the AI product with like IDAC DoD department mainly. And then when I moved to UH, I had the chance to work like with the physics team, quantum. They have some project in quantum research. I take care of the machine learning and computer vision part for them, and the public health center. So I take care of the AI component on the project they have there. So a little bit more about the campus. So you may not really know where is the I can say, so give you the quick point. So it's Texas, Dallas, you ride about 3 hours to the north is my main campus. So easier you can find like the campus is the hometown of Walmart and JB Hunt. JB Hunt is one of the popular truck company in US. Logistics, yeah. So 5 topic I really focus in my lab, and these days biometric privacy, which is have been worked for more than 15 years. AV mainly for perception. Smart health. The last 2 one is precision agriculture and quantum. I just like focus less than 5 years when I moved to U8. So here some classical problem in computer vision and image understanding. So as you know, we have the input image and video, and then in the classical way, we have to go to the encoder feature structure. Everyone know that, and then you have the feature, and then you go to the decoder or the classifier, and then you have the decision. This is the traditional computer vision they usually go through for image understanding. And the traditional way we usually use like shift feature, right? Better work. And the classifier in the traditional way, the KNN SVM based model, right? For the modern approach, we combine them together. We have the encoder feature extraction and the decoder go together, and we train end to end. Now the feature is not the handcraft feature anymore, but we combine with the classifier, and so that it can optimize the feature and the decision making. So I will come back to that framework and why we talk about that. But here's something you see, you can find social media, Tesla, they draw and then they see some new scene object, right? Moving. So you can see the wrong detection, right? It's clearly because in the real world, corner case is always the problem, right? You cannot collect the data, everything in the world for sure, right? And this is happened to the product already deployed and used in practice these days. I will talk more about that. Tesla, they cost a lot of money for data collection. They have the army to collect the data, not only US, but in the other country as well, the labeling. Because of that, the annotation is too much expensive. The company, they can make it, but how about the research side? Do we have any other way to make it better? And the second is, even though they spend a lot of money for data collection and labeling, but it's still unfair prediction. You can detect the car in common car pretty good, but one day you see the new object like corner case, right away they have wrong detection. Well, how can we solve it? And the next thing, new objects.
Why do you call this unfair prediction? That's what.
Yeah, unfair mean like they say something similar but not exactly.
Oh, okay.
Yeah.
Unfair.
Yeah, okay. Unfair prediction. But it is a never seen. It means like the one they see that it's a misunderstanding what someone already have in the training set. That is something really happen in the product in the market at the moment. And how can we are in the academia, right? We want to use like the advanced deep learning computer vision to approach it. Then we consider 3-4 cases happen in practice. The first one is require a lot of large scale data. Second, in the bias, produce the bias in the prediction and cannot handle the new class. And more important, in the open work, right? When the deployment, we always see the new cases. How can we handle that? With that in mind, that define my the research roadmap for the perception in my lab. And the end goal in my vision is that how can we develop the perception, understand the new object, the scene in open work environment. And for sure, we cannot train the supervised learning case. It have to be open work, have to be fairness and continual learning environment. And we have recently some correspondence work study corresponding to like for the topic. We do have unsupervised domain adaptation to try to address the labeling large scale data labeling problem, and then finish domain adaptation learning for the bias prediction. For the novel class, we have the fairness continuous learning, and the last one is for the open work fairness continuous learning. We have upcoming work. Just a quick reminder, everyone here already know about us. In the AV, we have 5 levels, right? So level 5 is the maximum. You can put the car anywhere and it can drive by itself. Level 4 within limited condition, a little bit like high automation. Tesla is somewhere in, they keep claiming they are in the autonomous self-driving car, but actually in the document, if you see that clearly, they put in 0.5. The difference here, the boundary is below level 3, the responsibility belongs to the driver. Above is the car have to take care, the company have to take care of the safety. So when the accident happen, whatever happened, Tesla, they don't responsible for that. That is the main difference. In order to reach the higher level here, perception is one of the key things. It's how to see, understand the thing. For my background a bit, beside academia, I had the chance to have the company put into the production for the perception component as well. In the perception for the core technology, we have to, the critical thing, the lane detection, have to be perfect.
Can you create smaller those names on that?
Sorry, which one? This one?
Yeah.
This one? Okay. All right.
Oh,
yeah. Then the lens segmentation, we have to understand what happened in the scene in front of us, and then we have to detect the object. But detect is one thing, but have to understand the distance from the object, which is the critical thing for the decision making. Free space detection to give us the idea what we can do within the limited space when driving. Parking light detection is important component, like give us the idea how to planning for the auto parking. Traffic light detection is important. I think this task is Tesla do a really good job actually. DMS, driver monitoring system, help the driver for the safety issue. And 360 view, which is most of the company now, they have this feature like top view, surrounding view. Localization mapping, a little bit go beyond the perception, prediction, trajectory planning, etc. But this component is more about perception, prediction, localization team. All right, so get back to the research. Before 20, there are for sure AV in perception has been worked for a while. But in this limit of the talk today, I try to focus our work from 2021 until now and what we do next with the advanced and recent methods in machine learning and especially for deep learning. And once again, we target to perception work in the open work environment. And then that is for the decision. The other component have to be good enough in the feature. Classification is good, detection classification is good, but on the other hand, we want to understand more about the characteristics of the feature. So based on that, we need to have the really good feature representation. Sometimes it's not only the image, but also the audio. Now perception is about what they see, but how about what they hear as well, right? Because we can hear the horn or beep beep from the car. Sometimes we have to send that, right? How can we incorporate into the perception because we want to simulate the human capability for the car driving? How about that? And then instead of frame by frame, can we incorporate to the video or temporal learning altogether? That's all the idea for the feature tuning, like robust presentation, multimodality. We are using deep learning, we know that. And most of the idea we talk about this is the deep feature, but how about had a better explanation for the feature? It's very important because it will relate it to the safety. Whenever you develop the technology, before you deploy to the user, you have to pass the safety issue. People will ask us, what does it mean? What is the upper bound, lower bound the solution? That's important. Multimodality for the feature representation and temporal. How about the cross view representation as well? So can we see from our view, from the top view, etc. That is about the feature. According to these 4 tasks, we do have the robust feature representation, multimodality learning, efficient for temporal learning, and the last one is the cross view robust representation. And put into the map together. One, you can see the above is for the learning and recognition, understanding. The bottom one is about the feature representation. Now we go to one by one. So as you know, domain adaptation is one of the common way people use to approach the data labeling problem. Input usually is like we don't have to use the real world data, but the simulation. One of the students here just work on it, right? And we train on simulation. In simulation, you can generate as much data as you want with the label. Data you can collect, but the label is the cost, right? Cost a lot. That is the traditional way, supervised learning. And then when you just like put what model learn on the real world, right? And if you just use like direct transfer without fine tuning the weight in the future, then it may have some not receive the good result. Obviously, because it's the different input, right? And the performance is not like what we expect. Then in domain adaptation, in the prior work, what they use is they use the entropy. They minimize the entropy loss. That is from last CVPR before our work. We use like the baseline. They have some limitation for the entropy. First, the assumption is pixel independent, but actually it's not. When we see the scene, we don't see every single pixel, but we see the meaning of the whole area altogether. That is the first limitation in the entropy minimalization. And they don't consider the global structure of the scene. They ignore that. And the last one is some areas may have another another image have the same one, but they don't take into account that point. Because of that, it has the limitation. And the result is insufficient. So based on that, those limitations, we come up with our own domain adaptation approach. We introduce a new way to measure the score. Let's say in unaligned domain, how the score should be. We come up with the loss function in a deep network. We call the bijective maximum likelihood or the BMR. The loss here have some feature, interesting feature. It's the bijective map. You have the image. You can extract the feature or the distribution. From the distribution, you can go back to the feature, the original image. And we can preserve the global structure in the modeling. And more important than that, in order to get the good result, the accuracy has to be good enough. So we got the state-of-the-art performance at that time on the standard perception, segmentation, understanding benchmark. Here's quick recap about the methods. We have the setup like image and the ground truth. We go through the bijective network, but instead of have the detection result, so we model in the distribution. So here is the network we call bijective network F with the setup parameter input is Y and the output in latent space Z. And we have the way to model the distribution it. And like I just mentioned, previous one, in our way, we can produce one-to-one mapping. The difference here, if you use the standard CNN, you have the image, you train to have the result. But from the result segmentation, you cannot go back to the original image. But we can do that in our proposed network. So that's why we call it bijective network. And it can keep the global structure. So now, with that in mind, given like simulation data, and we can have the data, the label, the prediction label, that we can train the network for the route route and the prediction result. Then we have the target domain, which is the real world image, right? So different from the simulation, and we have the prediction result on the real world or the target. And then now we can measure in the distribution the loss we define. Going to a little bit more about the loss, we propose there are some property this can is modeled by the flow-based model. We don't have the pixel independent assumption, and it can keep the global and both global and local structure. About the mathematical approach, we can demonstrate our loss, which is the upper bound of the entropy loss, which is the prior work. So which is more generalized than the previous one. And here's some results. So you can see the input with our adaptation and prior work here. Our results here for segmentation. This work we work in 21. So later on we have some improvement. Then let's talk about the fairness. This is what has been done, right? What does it mean about the fairness? Fairness means, let's say it's the scene you see, right? And you see the rod, the number of pixels. You see the rod like it's much more than the number of like the gen you see the bike, right? The building you see more than like the truck, etc. So you see some class, you see the instant is much more than the other class. It's obvious the is bias problem, right? The scene here, or the minority group, right? Like very rare pixel happen. Even though you want it balanced, you cannot make it in practice, right? The more you collect the data, the more the pixel for the road and building you see, right? You cannot make it in the real world. So the only way is you have to come up with the good machine learning approach to handle that. How can we model the bias problem? And in CVPR this year, we introduced the methods we call the freedom. In freedom, the interesting thing is we propose a class relevant fairness for semantic segmentation. We propose the fairness domain adaptation approach to this problem, promote the fairness, right? Improve the consistencies in the model, and more important, conditional structure constraint for the network. And performance, because we look at the less pixels classes too as well, we can achieve the better performance than the other class, which is quite biased. The ways the methods do is just like this. We have the source domain and the target domain. That we already know. We have the segmentation network like we present before, and we have this propose the supervised loss, adaptation loss, major group like car, truck, the building, the minority group like the human, the bicycle, right? And then we propose the conditional structure network to constrain the conditional constraint loss altogether. The results, after we consider on the less instant pixel class altogether, the result even further improve compared with like our prior work 21 here. So more results you can see in the paper. So what's the next? So now, even though we know it's fairness in domain adaptation, however, we keep seeing the new thing, right? The new scene coming up. The always still supervised learning. Supervised learning it means the closest problem. So, however, what happened? We want to have the perception just similar to the human way. We keep learning, seeing the new stuff. Because of that, in NIPS this year, 23, we come up with the methods we call fairness continuous learning. What we want to do is different from the prior work. We accept to see the new scene. And when we see the new scene, we have the reasoning, what happened, what is this? For example, here we can see the new unseen class. And then we have 3 steps here, for example. In step 2, we only see the label for the trend. However, in step 3, we see the label for the scooter. And then we approach it in the continuous learning way. In continuous learning ways, there are 2 fundamental problems. The first one is called catapultic forgetting, which is whenever you see the model, when you update it the second time, the third time, the model, the knowledge you learned before will be forget. So that's the first problem. The second is the background shifting, which is the label previous and the future step may be collapsed together. In this work, NIPS 23, we further introduce one feature, which is the fairness in continuous learning. Think about this. Let's say you have 5 classes you already learned in the model. And then let's say when we ride a car on the highway, you see the new unseen class, but you just see one new instant at that time. You don't have the 100 sample at that time to incorporate to the model, just one instant. And because of that, if you put into the model, you learn together. Again, this will have the bias problem. That is the major issue. People didn't see that in continuous learning until our work this time. And then we introduce the finished continuous learning. The first one is cross entropy loss, just like the standard loss in segmentation. We do introduce the finished objective class distribution when we try to measure the finished feature. And similar to the previous work, we also have conditional structure consistency objective loss, which is modeled by using the Markovian approach. Here is the simple way. So you can see after we model the distribution on the unknown class, we'll have one cluster, then we have the cluster of car and tree and the building all together. Here's some result we have done using fair continuous learning and the continuous learning without continuous learning. So you see it can do better job or even approach scene. So obstacle model. So we keep seeing the new stuff in the open work environment on off-road data. We cannot label it, just like Tesla they do for their perception. That's what we have done up to 23. And what next? So keep going with the story, finish, continuous learning. And what happened in the open work? Open work, we mean what this mean is, so far we for the car, tree, building thing we already see, then that's fine. For the other thing we haven't seen, we call it unknown class. But what happened with the unknown? We want to have some further work to better deeper understand about unknown. That's okay to haven't seen let's say the bike or the motorbike before, but it should be two different unknown class. And that is our current work in CPBR 24. They submit in this November. We further deep dive into this group, understand about unknown class. That is the roadmap for the perception. Once again, this is our last work, latest work for off-road perception. That is about decision for classification and segmentation. So for the feature understanding, this is the traditional way. Whenever we do, given the phase, we want to do detection or classification. Usually we have to extract the feature and then you use the cosine distance to measure two phase similar or not. In 2020, we had a crazy idea. I asked my student at that time, given the feature input, this feature, can we reconstruct the original phase? That is original idea I gave it to them. And we turn out we can propose the interesting work at that time, 2020. So we used our modified GAN model to approach this problem. So for the purpose presentation, with the traditional way, with the pixel loss, they use the direct metric, which is impossible to approach this problem, because two phase of the same person. If you use just like the pixel loss, you cannot say they're the same person, and not have to be the semantic space. The classifier-based metric doesn't work as well. It's indirect metric in the latent space, limit in terms of the image quality. May different image compared to the route root. And in this work, in CPBR 20, we propose the bijective metric, try to measure what is the similar between two phase with the same subject when they reconstruct. And the more important, how can we reserve the identity of the subject? And we benchmark on the standard data set. Given to the route root and the phase reconstruct phase, we try to map it into the latent space for the distribution. And then we compare on that. That is the idea. We go with like both the white box and the black box model. White box is mean you know what algorithm, deep learning model, and backbone you implement. Black box is you even don't know what kind of face recognition algorithm they implement. You just know the feature, and then you want to reconstruct with the given the input feature. How can we reconstruct it? So the first one is some prior work before our just like standard GAN. The second is our work. The last one is the raw truth. That is for the feature robustness. And then when we have the multi-modality learning, when we have more than just the image, let's say we have the audio visual together, what can we do? We propose the methods we call audio visual transformer to interaction between the speaker in video scene. And then also the audio correlation to model the flow, audio visual for the feature mask extraction. And then we do alignment in the main step here for cross-domain approach. New circle synchronization loss, try to make the models more robust in self-supervised learning manner. And benchmark on the standard data sets. So now we have the video, the visual feature and the audio on together. We go through the feature for the visual correlation, audio correlation, and then we do domain alignment on onto the subspace together. And then we find the audio visual correlation on the top. So here's some result. So the idea is, let's say in the video, it may be used for video calling. My original days, that is COVID time. A lot of people using the teleconference in those days. So for the elder people in the conference, that's very nice, no problem. But I look at my children, and at that time they still have online class as well, and it's just like crazy. Everyone talk like my children. And my idea is, how can we know who is the main speaker and give them the chance to talk? The other, we cancel their voice. That is the idea. And with that result, we can make it. So let's say is the original.
Make it work again.
Well, he approved NAFTA.
New jobs, a balanced budget,
which is the single worst trade deal ever approved in this country.
Incomes went up for everybody.
Sometimes the two people
I think
speak at the same time.
Worked and how we can make it work again. 3 million.
And then we can use the visual feature and the audio together, try to understand who is the main speaker. And then we give the permission to the main speaker to talk, and we cancel the voice.
New jobs, a balanced budget, and incomes went up for everybody. Manufacturing.
Yeah. Or some
Port Rock, who's 26, was at home at this house behind me here in Les Murdy. Who's 26 was at home at this house behind me here in Les Murdy.
a teleconference, same.
And is available on iPhone for both clients and for professionals. Is that correct?
Correct. Yeah. So unfortunately, we didn't see coronavirus coming. So Android is in the roadmap, but at the moment,
and is available on iPhone for both clients and
That's it for multi-modality learning, combined between visual and audio together. And then the next thing for the temporal learning. Temporal learning means we consider video. Video is the multiple frame. So we have the very simple idea. What happens if video, they have its own structure. What happens if we shuffle the position every frame in a random position and ask the network to reconstruct to the right order? And then at that time, the network will be strengthened. On the way will be strengthened, have a better understanding about the meaning of the video. That is the basic idea in this approach. So let's say you had a bunch of input video, you package to like the latent space after you use the deep network. And we go through the videos, deep model video. We call it the direct former. So one for just like classification for action recognition or prediction. The other, the second one, also the novelty in the work is the other projection. How can we redesign? So is the other projection can reconstruct the order of the video frame. So we have the component to make it. We can directed component attention. So try to reconstruct the order in the spatial and the temporal space. And then we have some shell attention for the loss function and apply for the action recognition. So you can see here, the methods can very good in target on the main actor, like riding a bike. So they know the subject can ride a bike. Those kind of stuff, I think important. When I chat with like one of our own very long time collaborator in Aurora. Aurora is the company they acquire Uber ITZ. So this is something they want to make from R&D team. They say sometimes they ride a car on the road and they see the people change the type, do some stuff on road. They want to understand those kind of action. And those methods will be very potential. Some statistical number, the proposed methods in the paper CVPR 22, we achieve good performance. Why here the accuracy? X is the computation. So X is the computation, less computation, but good accuracies. So far, we have introduced on the roadmap for learning, making decision, and the feature, the probability feature. And the last one we are currently working on is we kind of cross-view robust representation. So we know if we have the camera, surveillance camera, we conduct a third view. What happens if we collect the data from the third view, but we can transfer and see from the first view, which is usually we have something like GoPro camera in front of the head. So can we use those data, apply on this data, and it's still workable? So this, for sure, we know they have some constraint about geometries. The research question here, how to model the cross-view correlation to learn a robust presentation across view. That's come from my crazy idea. Let's say you can mount camera on in front of your car and collect a bunch of like data with the route truth, right? Then you train an AI model. Then what happened is what happened if I apply that model and we use the view from the drone? As the drone recognize it, is it still doable without training from the drone view? Just use the perception we train from the car view. Can we make it feasible? That is my research question. And everyone knows that right away about data collection. We cannot collect like both the scene, see from the car and the drone at the same time. That's impossible. Very hard to make it well alignment, right? We know it's hard. And because of that, that's come up with the research question. We have some initial work on this in CVPI this year. We have some mathematical model based on the geometry constraint. We come up with the result. We train the perception from the car view, and then we can see, make it run on the drone view. So you can see here the others view of the building like this for sure, because the car never see that the top of the building, so they don't make the decision. However, the road, the car, or the bike, the people, it still have some similarity there. That's why they can do detection and segmentation. So this is still the current ongoing work, and we plan to have it later this year. So far, what I have introduced you see, even though the deep learning there, people have achieved a good performance, but still a lot of things we want to open up the box. We don't want to use like deep learning like the black box. We want to use like the white box. We want to understand what happened with the decision. This is explainable. Also, the feature has to be robust and have to be reasonable in the way we present it. That's important for us. In the other days about the safety for driving. So beside the car, I have a couple of quick slides for trucking, which is another topic we have in work in last few years. So in our CVIU lab, we also target on the single camera object tracking, single camera, single object tracking, like driver monitoring system or single camera, multi-object tracking with a single camera, or multi-camera, multi-object tracking, or you deploy the tracking but on an embedded device. That's more about the optimization. And then multi-camera, multi-object tracking, but on the move, right? When we mount the sensor on car. So it's something we done 2017, like track the phase input, like 2D input from the any webcam quality, but we can reconstruct the 3D structure of the face, and we do like facial expression understanding. That's it for facial expression 3D reconstruction. Then we have in CVPR this year we had a method we call a micron burst. We try to understand not only the expression but also the micro expression with the minor change on face. For example, in this case, can you see where is the face area change? It's a very minor area here, right? Our methods can spot it very well. Meanwhile, the prior work cannot make it happen. The second case, even harder. Keep in mind, this we had already slowed down many times, so that we can see that in the real world, it's very hard to identify it. And we propose the micron work to approach it. That's for the face and tracking of the face. Then for surveillance camera, we have multi-camera, multi-object tracking. This problem is, let's say we have 3 cameras, we have to make sure the consistent across one camera, but also across like multi-camera here. So you can see in case we have 4 camera, look at the cyclist here. So the cyclist, the ID have to be consistent, not only from one camera, but also from multi-camera here. That is multi-camera, multi-object tracking. That is for overlap field of view case. Then we have the case of like non-overlap field of view, where one camera inside house, one camera garage parking lot. So the subject go through the camera and see in the second camera. It has to be consistent for the ID. And then in the third camera, there's some new subject coming up, so I have to assign the new ID. So that's on the whole idea. The same idea, but we just extract the different feature. Now we can apply for vehicle tracking. So grab base is still there for tracking, multi-camera, multi-object tracking is still there. But just like this feature, now we use for car. Then multi-camera, multi-object tracking, we know from new scene, right? We have 6 cameras, 3 in front, 2 side, and 1 back. So, but it's on the move. Only different is on the move. So you can see our methods can be consistent. The same color is the ID. So the prior work, they change the ID, which is the fail for tracking. Is something we done. And then in NIPS this year is coming up in this December. We just got the results. Now let's say we want to track the subject, but in flexible way. We combine with language model. Let's say now we want to can type in the ChatGPT style, but ChatGPT for language only. We have the way to let the ChatGPT or language model to understand the meaning of the video. So we can track for the on people with like the query here or the from here. Or in case we want say just follow the man with the suit. So in order to make it, this feature have to be able to understand the meaning of the feature they are using. So this is some kind of like frontier work in the tracking. We haven't seen prior work in this topic before until our work. So let's say focus on the way cost suit man. Just focus on this one. So this is some kind of very flexible. In traditional way, you have to retrain the whole model. we don't need to do that. And that is one of my last slide about the technical one. And this work cannot be done without supporting of the team. We have amazing student, very active student. At the moment, I have 7 PhD, 1 master, 7 undergrad. That not too crowded, but good enough, make me busy. And we organize the workshop, publish the source code, like the paper, something that you see, you can go to GitHub on my lab and can try to test the code. And we're very open for the collaboration as well. The recent work I just mentioned, the last is tracking in combination with the language model. We also publish the data set, and the model there is coming soon. And that's all. Thank you so much.
Thank you. I mentioned to you guys that this group, let's get 2 people, 7 news. Sometimes you see that I think it's ideal, right? You might like this, just a combination of language models. It's kind of cool. But this is exactly what I recall last time when I visited China. There's a guy. Can we find the guy who is on the motorcycle?
Yeah.
Exactly. There's a huge need. I think that's pretty cool. Okay. We want to make this more interactive. We just have 3 vision expert coming here. So why don't you guys introduce yourself? Sit. Introduce yourself so that he knows who you are and where you're working.
Hi, everyone. I'm a fourth-year PhD working with doctors.
Keep it real.
Yeah, keep real.
Real name, but keep real.
Currently, I'm working on everything. So I used to be working on the legal like long time. I also do something like doing more and more legal stuff, but I'm working on state time. So now I'm doing everything.
I see. That's interesting.
Very good time.
Sure. Thank you.
I'm also in the same lab as mine. So we work with my project is on we work with the street for the years of consultation in the region. I spot some very relevant topics that we talked about because I also looked at those when I first started my PhD. On 30 years ago, and I'm very interested in the normalizing flow because I used to look at like evolving the movement application, how can we adapt the model over time. So I was thinking about like applying normalizing.
Yeah, that is beautiful methods because it guarantee the projective feature like property.
Yeah, right, but the thing is, if you go out of it, it's not guaranteed that the evolving pattern will be linear or consistent.
Yeah,
that will probably break the whole.
Right, and also the design quite tricky.
Right, and I think it's a pretty ill posed problem. It's
yeah,
but
I'm Xu Chao. I'm from Course. Back from Stanford here. It's my first time in this building. I'm very proud to be building.
He's a post student. You met Paul yesterday. He actually is from main campus, all the way coming here.
Thank you for coming.
So yeah, I'm working on right. I'm also first year, so right now I'm not working on this particular project, but just I'm thinking I'm gonna do some kind of semantic stuff, like imagine like semantic
I see. Yeah.
So interested in your work and I want to like go a little deeper. I'm not sure if we have something, but like from the image, it looks like the adaptation, like does that happen some city state?
Yeah, we use city scan.
I want to know like I do some details like that one and you mentioned like you can transfer some data from simulation to real one.
Mhm.
So I want to like what is the kind of performance and like I see something visualization that looks really good. I wonder.
So we also have some numbers for sure. When we go to the paper, we have to go through not only one data set but like multiple data set to make sure the result won't be like overfitting. So we use on the data sets in senior standard. People usually use CT scans is one of them.
Oh, so I wonder the setting would be, the training happens all on the simulation and directly transfer or it's a combination of the.
The domain adaptation, I believe they already have the standard protocol there. You have to, when you claim your method is good enough, you have to go through the protocol. What data set you use to train, what data set you use to test. If you're interested, you can look at the paper and feel free to email me.
Like I also would like to make the insight that we using in general that is people to do like just everything seems to make it set and performing tasks in the real world using that like that is possible or some kind of you have to get some real data and then do some small multiplication.
Okay, maybe I'm not really clear about the question, but
my question is using it possible, I have a new task for new class. I don't have any real world data, so I want to train the whole model, without any base class. I think purely on this.
So there are two approaches. One is you use like domain adaptation, right?
Yeah.
You have some data. The later work, we focus on, maybe I stay here so the other student can hear me from Zoom too. The recent work from 22 to 23 and the upcoming one, we switch to the contour learning. Contour learning, what you see is what you get. We don't use the simulation. For sure, in the first frame, you see the new object. They say they don't know, but that's fine. Put them in one spot there. Second time, they say, okay, also new, but similar to the first one I see. So we put them together. For sure, we don't know exactly what is the name for that class because we not really label, but we know that's in the same group. That's the goal. I hope I answer the question. It doesn't matter. It's say bike, motorbike. Even if you see two bikes, it should be the same group. That's the goal. Yeah.
Questions from this side?
Sorry, can you repeat the question? Oh, multi-model, we haven't used like continual learning approach yet. Yeah, but just like for understanding. Yeah, we can do that. Yeah. 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 We may need more students to work on it. Too many things. But yeah, that should be the next topic, potential next topic. Yeah. Yes, please.
Is the models as effective in lowlands
Again?
You're not.
So domain adaptation have to be handled that. Actually, in two sides. One you approach in the production side, one in the research side. That is very different. In the production, you have to care about the camera, fine tuning on the sensor, right? That's one of the common one, and we know some staff working on it, right? And you have to do image processing, pre-processing. That's the whole the industry they're doing the real work. On the other side, the machine learning and AI, we talk about research. Then the domain adaptation have to be generalized enough to cover different kind of like weather environment or the lighting condition. As we call the robustness in the future, like two sides. So the beautiful thing is both of them can meet somewhere. But sometimes the product they have to go with engineering quite a lot. One is we try to optimize the learning. I hope to answer the question. Yeah.
No question?
Yeah.
Like, this is more very technical question, but because I noticed, in continual learning, we care about fairness more than like catastrophic event other problems. Like, I mean, the word, but
Okay.
what is more, so I just want to ask it, what is your go-to, method when it comes to preventing?
Okay.
catastrophic?
I got the question. So for the fairness, we would say we keep on the current requirement, the forgettings and the shift, domain shift, we have to be the same, but the novel is the fairness,
Right.
put them together.
Right.
We don't
Like,
satisfy.
What is your go-to, like?
Oh, the
methods for
vision.
for those, There's gonna be like method based.
Oh,
You just benchmark on all of.
so the goal will be how we have the perception can see the stuff in the fair way. That's the goal. Because think about if you already have one trained model, with five class, each class you have 100 sample already there. You train, right? You have the model. Then when you deploy in a continual learning way, then you see the new class, okay? But you just see one sample. If you put them to train to update the model, it will be unfair, right?
Right.
That's the problem. Yeah. And we try to address that problem. But for sure, we have to maintain the forgetting, and then the domain shift. Yeah. Yes, please.
And the interesting from tracking paper.
Tracking.
So you get in words like, you have to train the whole model, right?
Mhm.
Is a large language model or just transformer or big reality?
So we use attention mechanism. We use multimodality and contribute. There are in that work we have two contributions. One is the data set. We have the team to label the data set, language model description for on the video frame. And on the technical side, the design, we have the way when we go. Now it's not one input, but we have two input, language and the vision together, right? So because of that, the attention metric is not a metric anymore. It's become attention, and the cost for computation cost is very big. So we propose a way to simplify it.
Multimodal input, right? So your model is telling about can take image and the prompt.
Yeah.
So my question is.
Not image, that's video.
Oh, it's a video.
Yeah.
Right? How can you use any prompt or you have to fix?
We use any form at the moment.
Okay.
But for sure, there's some form work very good. Some form is not really good.
The prompt is not from for like training data.
Yeah, no, yeah, you don't have to be from the training.
Okay.
Yeah. But for sure, some form is not really
If
perfect.
you use very prompt, just the keywords in the good or.
We have on evaluation when it's good, when it doesn't work. But the limit for the Archimedia is somewhere we cannot have the really huge training data sets like Google or Facebook. They publish a ton of data, right? We just have some boundaries there. Mm-hmm. The methods, if you have more data, you can apply the model to upgrade the quality. Yeah.
Off of that, I was thinking about, what if you fix the text encoder and trying to align the vision encoder with the text encoder, then you can still leverage, the very rich knowledge that the language model provide. But because we all know like the business code is always small, so maybe in that way, you don't have to train both modalities.
So alignment is one of the topic I keep mentioning to my students. Alignment between the language and vision.
Right.
In some way, the way they do in the technical side is still quite simple. That is I see that's still a lot of open room to further investigate.
CVPR 2024.
Yeah.
Both of I and I are the area chairs, actually, so we
Yeah.
were, I guess all the autonomous vehicle people will be in our camp. You guys gonna help us to do the review, okay? I don't have enough time to deal with all these things. Okay, well, thank you so much.
Thank you everyone.
Yeah, let's go. Thank you guys for coming, particularly from Spain.